Welcome to Slow Science Sleep, the channel where the vast, mysterious universe meets gentle storytelling, all designed to help you relax, drift off, or simply wander through scientific wonderlands at your own pace. Tonight, we're heading straight into the shadows of the cosmos, where light disappears, time loses its meaning, and gravity becomes almost ridiculous. Yes, tonight's journey is into the strange reality of black holes, and more specifically, how these cosmic oddities stretch space and time itself. Thank you for watching. And I'm sorry if this ends up being too exciting or too mind-twisting to let you fall asleep easily. Please consider liking this video, subscribing to the channel, and commenting where and what time you're tuning in from your city, your time zone, or even your galaxy if you're feeling ambitious. Now, let's begin the story. It starts with the idea of space as more than emptiness. Space is not a void. It's more like a fabric, flexible, stretchable, and astonishingly obedient to mass. When Einstein introduced general relativity in 1915, he flipped our understanding of the universe. Gravity wasn't a force pulling things together. It was the result of mass bending space and time. And few things bend space and time more aggressively than black holes. To understand black holes, we need to first understand the fate of stars. A star like our Sun burns hydrogen in its core for billions of years, maintaining a delicate balance between gravitational collapse and nuclear fusion pushing outward. But when the fuel runs out, gravity wins. If the star is massive enough, more than about 20 times the mass of our Sun, the collapse doesn't stop at a white dwarf or even a neutron star. It goes further, folding in on itself until what remains is a singularity, a point of infinite density surrounded by an event horizon. The event horizon is where things get truly weird. Not because it's violent or chaotic, although it can be, but because it marks a one-way door in space-time. Cross it, and escape becomes impossible. Even light, the speed limit of the universe, has no way out. The radius of this horizon is called the Schwarzschild radius. For a black hole with the mass of our Sun, that radius would be just under 3 kilometers. Imagine compressing an entire Sun into a sphere barely larger than a city park. Now imagine compressing more. The larger the black hole, the more intense its grip on space and time. But here's the mind-bending part. From the outside, it's not about the mass alone. It's about what mass does to space-time. The more massive an object, the deeper the well it creates in this invisible fabric. A planet like Earth curves space-time. Modestly, the Sun makes a bigger dip, but a black hole, it stretches the fabric so deeply that the geometry changes fundamentally. Time slows down, distances become distorted, and simple concepts like before and after start losing their meaning. This is not science fiction. In 1976, scientists used precise atomic clocks to test Einstein's predictions. They flew one clock aboard a plane while another remained on the ground. The airborne clock, experiencing slightly less gravity and moving quickly, ticked at a different rate. The difference was tiny, but measurable. It proved that gravity really does alter time. So imagine the difference near a black hole, where gravity isn't just stronger, it's off the charts. If you could hover just above the event horizon, assuming you had some absurdly strong propulsion system to keep you from falling in, time for you would pass more slowly compared to a person far away from the black hole. This isn't a metaphor. If you spent an hour floating there, people back on Earth might experience years. It's as if the black hole reaches out and stretches time like dough under a cosmic rolling pin. But time isn't the only thing under stress. Space itself bends, twists, and warps. If you dropped a probe toward a black hole, you'd see it accelerate, then appear to freeze as it approached the event horizon. It would seem too slow to a stop, dimming and reddening as the light stretched, unable to escape. To an outside observer, It never quite falls in, but to the probe or the poor astronaut in it, the crossing would be uneventful. That's the odd charm of black holes. They're mysterious, but also deeply unfair to human intuition. And what of the inside? Number? One knows for sure. The singularity is where our theories break down. Matter crushed to infinite density. Time and space compressed into a zero-volume knot. General relativity tells us it happens. Quantum physics says, hold on, that's impossible. The two great theories of modern physics argue here, like siblings in the backseat of a long drive. We need a theory of quantum gravity to settle the score, but so far, nature has kept that particular recipe secret. Still, black holes keep offering clues. In the 1970s, Stephen Hawking made a shocking prediction. Black holes might not be completely black. Thanks to quantum effects near the event horizon, particles could escape. This Hawking radiation would slowly drain a black hole of energy, causing it to evaporate over time. Not fast, not by any stretch. A stellar mass black hole would take far longer than the age of the universe to disappear. But it gave us hope. Maybe black holes don't just consume. Maybe they also reveal. And maybe, just maybe, they open the door to new physics. The relationship between black holes and time is where things get especially entertaining. In 2006, scientists analyzed X-ray signals from stars orbiting a black hole called Sagittarius A*, the supermassive black hole at the center of our galaxy. The data revealed the gravitational redshift effect, where time-stretched light becomes redder. The same process is at work when astronauts aboard the International Space Station age, ever so slightly slower than we do on Earth. The idea of time. Dilation has practical uses too. GPS satellites, for instance, have to adjust for both the effects of speed and the weaker gravity of their higher altitude. If not, their navigation calculations would drift by several kilometers every day. So yes, the warping of space-time is not only real, it's part of why your phone knows where you are. But in the presence of a black hole, this effect ramps up from useful to absurd. The curvature becomes so intense that straight lines, the natural paths that objects follow through space-time, start curving inward. Once past the event horizon, all paths lead inward. Even light, which normally travels in straight lines, bends so far that it spirals toward the singularity. This creates a region from which nothing escapes, not just matter, but also information. And that leads us to one of the most dramatic debates in physics today, the black hole information paradox. If matter carries information and falls into a black hole, does that information vanish? If so, it violates the rules of quantum mechanics. If not, then where does it go? Some theories suggest it's encoded in the Hawking radiation. Others hint at strange quantum fuzz around the event horizon, or at hidden dimensions we can't yet see. The truth remains elusive, but one thing is clear. Black holes are the most extreme demonstration of how gravity bends the rules of space and time. They remind us that the universe is not a simple place, and that even the most basic elements, time passing, space being flat, can be undone by the presence of something massive enough and dense enough to rewrite the rules. Black holes are not merely cosmic vacuum cleaners, sucking everything into oblivion. They are exquisite natural laboratories that challenge the limits of physics and force us to reconsider our assumptions about reality. While their popular image often involves destruction, the more we study them, the more they resemble intricate puzzles wrapped in darkness. At the heart of every black hole is the singularity, a place where densities become infinite and our equations simply stop working. But here's the catch. No one has ever seen a singularity. It's cloaked behind the event horizon, hidden from the universe like a magician's secret compartment. General relativity predicts its existence with unnerving confidence, yet it's possible this infinite point is not real in the way we imagine, but rather a symbol of where our theories need fixing. To appreciate the drama of what happens near a black hole, let's visit the supermassive kind, the cosmic giants that anchor galaxies. Sagittarius A*, lurking at the center of the Milky Way, has a mass of about 4 million suns and a diameter, just over 20 million kilometers. That may sound huge, but remember, it holds the mass of millions of stars in a space smaller than the orbit of Mercury. The result is a gravitational field so powerful it reshapes the very flow of time for anything daring enough to approach. Near Sagittarius A*, the warping of time is not just a theoretical curiosity. In 2018, astronomers using the Very Large Telescope in Chile observed a star named S to swoop close to the black hole. As it neared, its light was stretched by the intense gravitational field redshifted exactly as predicted by Einstein's equations. It was the first direct observation of gravitational time dilation near a supermassive black hole. This star, racing through distorted spacetime, became an unwitting participant in a cosmic test of relativity. But what would it feel like to fall into a black hole, assuming you weren't instantly crushed, which depends on the size of the cis? I'll see me to be, only Ruby Kiss has the luxurious. Mayan sift, while my last by Casey's to Elisus, and live like why we win, what would it feel like? Long-lasting color. But what would it feel like to was me? You will win my sicht, our wise colludes lass, you see my lev. Why we a seeb? Why we see so f? Why we see my lass, I'm all at reese, pie we am my with us. I bree by kide. We mode, I'll see you I lisa tie, we so we sis at kai. We suk I says gully it's guns get it to be to buy as I tip use it to sit get it to sit it I stick to the and we put it to this to the second to this though it's black hole. You would experience a phenomenon charmingly known as spaghettification. This delightful term refers to the tidal forces at play. Tidal forces arise because gravity acts more strongly on parts of you that are closer to the black hole than on those farther away. Near a small black hole, this difference is so extreme that you would be stretched like a piece of cosmic pasta. In large black holes, the gradient is gentler near the event horizon, meaning you might not feel anything unusual as you cross that boundary. You'd float past it calmly, unaware that you'd just passed the point of no return. But the laws of physics would already be changing around you. Space and time would begin to swap roles in a way that sounds like science fiction, but is a mathematical reality. Inside the horizon, time leads you forward, toward the singularity as relentlessly as the passage of minutes in your living room. No propulsion, no clever maneuvering could change your fate. What lies beyond that moment is unknown. Some theories propose wormholes, shortcuts through spacetime, hiding within certain types of black holes. These ideas come from solutions to Einstein's equations known as Kerr black holes, which allow for rotation. If a black hole spins, as we expect most do, its geometry changes. Instead of a single point, the singularity becomes a ring. This opens theoretical passageways, sometimes called Einstein-Rosen bridges, through which, in principle, one could travel. But don't pack your bags just yet. These wormholes are unstable. The slightest perturbation could cause them to collapse, vaporizing any traveler into oblivion. Moreover, the energy conditions required to keep a wormhole open seem to demand negative mass or exotic matter, concepts that, so far, remain more science fiction than science. And yet, the equations tantalize us. They hint that space-time is more flexible than we ever imagined. If space can stretch and time can slow, perhaps there are pathways hidden in the folds of the universe, waiting to be discovered. It's this tension between the known and the unknown that makes black holes so irresistible. The extremes don't stop at size or gravity. Black holes also play a starring role in some of the most energetic events in the universe. When galaxies collide, their central black holes eventually spiral toward each other, merging in a cataclysmic event that sends ripples through spacetime, gravitational waves. First predicted by Einstein, these waves remained undetected for a century, until 2015, when the LIGO experiment captured the faint tremor of two black holes merging over 1 billion light-years away. This detection was not only a scientific milestone, but a poetic one. For the first time, humanity heard the universe ring like a bell. The gravitational wave signal lasted just a fraction of a second, yet carried more energy than the entire visible universe. The black holes that collided had masses of about 29 and 36 suns. Their merger released an energy equivalent to 3 solar masses, all converted into gravitational radiation. Think about that. 3 whole suns' worth of mass turned into pure waves in the fabric of spacetime. These waves are incredibly weak by the time they reach us. LIGO had to detect a distortion in space smaller than the width of a proton. Yet from that tiny wiggle, we learned about a collision that happened before life even existed on Earth. And since then, dozens more black hole mergers have been recorded, forming a new kind of astronomy that doesn't rely on light at all. It's like discovering hearing after spending your whole life in silence. Black holes don't just warp space and time. They've warped how we study the universe itself. And just when we thought we had understood their shadows, they offered us something new: a photograph. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole silhouette, captured in the galaxy M87. This blurry ring of fire, surrounding a dark core, was not a computer simulation or an artist's concept. It was the actual data stitched together from radio telescopes around the world. What we saw was not the black hole itself that's invisible. What we saw was the glowing gas swirling around the event horizon, moving at nearly the speed of light. This image, imperfect and smudged by noise, still carried a profound message. It showed us the outline of a shadow cast by gravity so intense that light itself could not escape. It was a portrait of where time stands still and space falls inward. The light took 55 million years to reach us, a whisper from a place where physics turns inside out. And yet, black holes are not monsters. They are inevitable. Any universe that allows stars must also allow black holes, because they are simply the final act in a star's life. They are not mistakes in the code of creation. They are features. Features that give rise to jets of energy that trigger star formation in galaxies, that hold galaxies together with their weight. Without black holes, our universe might look very different, perhaps even unrecognizably so. We once feared them. Now we seek them out. From quasars to X-ray binaries, from microquasars to gravitational lensing, black holes are not hiding anymore. They are teaching us about entropy, about quantum fields, about the limits of knowledge. They tell us that gravity isn't just a force, it's a sculptor of reality. As black holes stretch space and time, they don't do it quietly. They distort the very structure of the universe in ways that ripple far beyond their event horizons. This isn't just a metaphorical ripple. It's literal. Space-time is elastic, and black holes are its overachieving gymnasts, twisting and flipping and stretching the fabric of the cosmos with impossible flair. But before diving further into how they influence the universe, let's back up for a moment and consider what space-time really is. We talk about it as a fabric, but that word is a stand-in for something we barely understand. It's not a substance you can touch or fold with your hands. It has no texture, no color, no smell. Yet, every mass in the universe interacts with it constantly. Everything that has weight presses down on it. Everything that moves follows the curves it creates. Space and time are not separate ingredients in the universe's recipe. They are two aspects of a single, united reality. Time flows differently depending on where you are and how fast you're moving, and space bends in response to mass. This interconnectedness is why massive bodies like black holes don't just sit passively in space. They actively shape how time passes and how distances behave. A black hole is where this interconnection becomes extreme. Imagine dropping a clock toward a black hole. From a safe distance, you'd see it ticking more and more slowly the closer it gets to the event horizon. At some point, it appears to freeze entirely. To the falling clock, however, time feels perfectly normal. Seconds pass as usual, but the rest of the universe would seem to speed up, racing ahead while the clock creeps toward eternity. This isn't philosophical poetry, it's a physical consequence of extreme gravity. The deeper a clock falls into the gravitational well, the slower its time becomes relative to outside observers. This effect isn't exclusive to black holes, it's measurable. On Earth, GPS satellites experience slightly different time rates than devices on the ground due to weaker gravity at their altitude. Engineers have to adjust for this. If they didn't, your navigation system could be off by kilometers each day. But with black holes, the differences become extreme. Near a stellar mass black hole, time can stretch so much that 1 hour to someone hovering nearby might equal thousands of years elsewhere. This isn't hypothetical. It's one reason why black holes are sometimes jokingly referred to as natural time machines. Not because you can visit the past, but because they let you experience the future more quickly by skipping over it. Let's picture this in a cosmic setting. Suppose an astronaut gets too curious and orbits just outside a massive black hole's event horizon, using powerful thrusters to resist being pulled in. Meanwhile, their twin stays safely far away. After a brief orbit, the astronaut returns. For them, perhaps just a few hours have passed. For the twin, decades or centuries might have flown by. The astronaut hasn't aged much, but everything they once knew is now history. It's a real consequence of the way black holes stretch time. And it raises philosophical questions, too. Is time absolute? Does it pass the same for everyone? Clearly not. In the presence of black holes, time becomes personal. Now let's shift from time to space. Black holes do not just bend the ticking of clocks, they twist the paths of matter and light. If you shine a flashlight past a black hole, its beam will bend around the curve of space like a car skidding around a sharp turn. Light follows the path of least resistance, and in curved spacetime, that path is no longer straight. When light gets too close to a black hole, it can orbit the event horizon in a perfect circle. This region is known as the photon sphere. It lies just outside the event horizon and marks the last possible stable orbit for light. Try to imagine that, a beam of light circling endlessly, trapped not by mirrors, but by space itself. Even more mind-bending are gravitational lensing effects. When a black hole sits between a distant star and an observer, it acts like a lens, not because it has glass or curvature, but because its gravity bends the light around it. This can create multiple images of the same star or stretch it into arcs. In the case of perfect alignment, it produces something known as an Einstein ring, a luminous halo of light surrounding the black hole's dark core. We've observed these effects with telescopes. Some gravitational lenses have even allowed astronomers to peer at galaxies far behind the lensing objects that would otherwise be invisible. So, in an odd twist of fate, black holes help us see more of the universe by distorting it. Still, the most dramatic influence black holes exert might be on their surrounding environment. Consider the accretion disk, a glowing, swirling ring of gas and dust spiraling into the abyss. As this material accelerates toward the event horizon, it heats up to millions of degrees. Friction, magnetic fields, and shock waves turn the disk into a cosmic furnace, often outshining the rest of the galaxy. In fact, some of the brightest objects in the universe are powered by black holes. Quasars, for instance, are supermassive. Black holes in the centers of young galaxies devouring matter at a furious pace. Their radiation beams out across billions of light-years. One quasar, known as TON 618, is estimated to have a mass of more than 60 billion. Suns, its energy output could incinerate any solar system unlucky enough to wander too close. And still, the black hole itself remains invisible. The light we see comes from the desperate spiral of matter circling the drain. The moment that matter crosses the event horizon, it vanishes from view. Not gradually, not eventually, instantly. Not even the most powerful telescope could follow it past that boundary. It's like watching a leaf swirl toward a waterfall, only to disappear beneath the surface in an instant. This boundary, the event horizon, is not solid. It's not a surface in the traditional sense. It's a mathematical point of no return, a place where escape velocity exceeds the speed of light. Once you're inside, all paths lead inward. The only direction left is toward the singularity. And here's where physics begins to twitch nervously. At the singularity, densities are infinite, space-time curvature is infinite, and our understanding of cause and effect breaks down. General relativity gives us one prediction. Quantum mechanics gives us another. And the truth, as usual, is somewhere out there, probably laughing at us. Some physicists believe that singularities may not exist as infinite points, but rather as regions, where new laws of physics come into play. There may be some quantum structure that prevents the total collapse, or some exotic state of matter beyond anything we've yet imagined. Ideas like loop quantum gravity or string theory offer possible resolutions, but none are confirmed. So, black holes remain the wild frontier of physics, where the familiar rules are suspended and the edges of knowledge blur into shadow. They are not evil cosmic monsters. They are strange, beautiful consequences of the same physics that governs falling apples and orbiting moons. They are a test of mathematics, of theory, of imagination. And still, they stretch space and time in ways that no other object does. They remind us that the universe is not a place of rigid lines and predictable clocks. It is a place of curves, of flux, of gravity so intense it stops time, so focused it swallows light. The more we learn about black holes, the more they seem like keys to unlocking the secrets of the cosmos, and perhaps the nature of reality itself. Despite their darkness, black holes illuminate some of the most profound questions in physics. They are like mirrors held up to the universe, reflecting back not light, but mystery. Every attempt to understand them brings us closer to the edges of what science can explain, and, in doing so, challenges the very structure of our understanding. Nowhere is this more evident than in the ongoing struggle to reconcile the two dominant theories of the modern era: general relativity and quantum mechanics. On one side, general relativity is the champion of the large-scale universe. It describes how planets, orbits, stars, how galaxies swirl, and how massive objects like black holes curve space and time. On the other side, quantum mechanics governs the very small, atoms, particles, and the strange rules they follow, where uncertainty is king and probability rules behavior. Each theory works exceptionally well in its own domain, but bring them together, say in the center of a black hole, and they clash spectacularly. At the singularity, general relativity predicts infinite density and curvature. That's the equivalent of a mathematical alarm bell ringing. Nature doesn't seem to like infinities. They usually mean the theory has reached a limit. In the quantum world, however, nothing can be infinitely small or perfectly precise. The Heisenberg uncertainty principle ensures that certain pairs of properties like position and momentum cannot both be known with perfect accuracy. So, the very idea of a point of zero volume with infinite density simply doesn't make sense in the quantum realm. This has led physicists to believe that something must change at the Planck scale, the unimaginably tiny realm where gravity and quantum effects are equally powerful. Here, space and time may no longer be continuous, but granular or fluctuating. At these scales, some suspect that space itself might be composed of tiny loops, vibrating strings, or multidimensional membranes. The search for a quantum theory of gravity is, in many ways, a search to understand what happens inside black holes. Yet the outside of a black hole presents puzzles of its own. Take the information paradox. In classical physics, if you throw a book into a fire, the molecules are destroyed. But the information, in theory, is preserved in the smoke, ash, and light. In quantum mechanics, this principle goes further. Information about a system's original state can never be truly lost. But what happens when information falls into a black hole? According to Stephen Hawking's original prediction, black holes slowly evaporate through Hawking radiation, a quantum process that allows particles to escape just outside the event horizon. This radiation is random, doesn't seem to carry any of the original information about what fell in. Over trillions of years, the black hole would vanish, leaving no trace of its contents. If that's true, then information is truly lost, a devastating blow to quantum theory. This contradiction set off decades of debate. Hawking himself revised his view late in life, suggesting that information might be preserved after all, possibly encoded in subtle quantum fluctuations at the edge of the black hole. Other physicists proposed more exotic solutions, like the holographic principle, the idea that all the information about what's inside a black hole is somehow stored on its surface, like a cosmic hard drive etched into the event horizon. The holographic principle emerged from string theory and suggests a radical idea: that the three-dimensional world we experience might be a projection from a two-dimensional surface. If this is true, then black holes aren't just strange, they're clues to a deeper, more holographic nature of the universe itself. And yet, the debate rages on. Are black holes ultimate destroyers of information, or do they merely hide it in forms we haven't yet deciphered? Could quantum entanglement, that spooky connection between particles, offer an escape hatch for information trapped inside? Some have even suggested that every black hole might be connected to a white hole, a theoretical object that expels matter instead of absorbing it. In this view, a black hole doesn't destroy information but transports it elsewhere, perhaps even into another universe. But if black holes connect to other regions of space-time, are they bridges or prisons? Can anything at all, ever make it back out? So far, the answer remains a resounding no. Even the idea of a wormhole as a stable passageway is riddled with difficulties. The exotic matter required to prop it open would need negative energy density, something we've never observed in a lab, and only theorized in the context of phenomena like the Casimir effect. Even if we could harness it, the slightest disturbance, even a single photon, might be enough to collapse the wormhole instantly. But that hasn't stopped science fiction from embracing the concept. From movies to novels to video games, wormholes offer irresistible plot devices, allowing characters to leap across galaxies, skip through time, or hide inside cosmic cul-de-sacs. Real black holes, of course, are not so generous. They do not offer smooth rides or round trips. They pull and twist and stretch reality until it can barely hold its shape. Still, the very nature of a black hole as an information vault remains one of the most tantalizing mysteries in physics. The event horizon acts like a cosmic firewall, cloaking what's inside from the rest of the universe. But new theories propose that the surface might be more complex than previously thought. It could be composed of quantum bits, known as qubits, that fluctuate and interact in ways we don't yet understand. Even stranger is the idea that space-time itself might emerge from entanglement. That is, the very geometry of the universe could be a manifestation of quantum connections. In this view, black holes are not just warps in space-time. They are knots in the quantum web that underlies all of reality. So as we look deeper into black holes, we may find ourselves not only staring into the darkest regions of space, but also into the fundamental building blocks of existence. They are both a destination and a key black vaults that may unlock the secrets of everything from gravity to consciousness. And the more we study them, the more bizarre the possibilities become. Could black holes be seeds for new universes? Some theories suggest that when a black hole forms, the singularity may not simply collapse into nothingness, but rather bounce, triggering the expansion of a new bubble of space-time. In this way, our universe might be one of many, born not from a singular Big Bang, but from the death of another cosmos collapsing inward. This cosmological recycling raises dizzying questions. Are we living in a universe spawned by a black hole in another dimension? Are black holes the reproductive organs of multiverses? If so, might the laws of physics evolve through a form of cosmic natural selection, favoring universes that produce many black holes? As wild as it sounds, some physicists take this seriously. They suggest that black holes are the ultimate Darwinian mechanism, nature selecting universes with the most efficient black hole production. In that sense, we're not just observers of black holes. We might owe our existence to one. And yet, in all their complexity, black holes still behave according to elegant mathematical principles. They obey laws. They follow thermodynamic rules. They have entropy, temperature, even pressure. Their surfaces encode information. Their boundaries are defined with precision. They are monsters, yes, but they are rule-abiding monsters. They remind us that nature is not simple, that our deepest intuitions often fail at the edges of reality, that what seems paradoxical may one day seem obvious, and that, perhaps, the only true horizon is our own understanding. It's ironic that black holes, the very epitome of darkness and silence, are often the loudest voices in astrophysics. Not in the conventional sense. They don't scream or rumble with audible sound, but in the way they dominate our scientific imagination. Even though they emit no light, their influence glows across entire galaxies. Their existence shapes the cosmos on every scale, from the orbits of stars to the behavior of atoms near their fringes. And while they seem like cosmic endpoints, places where things go to disappear, they're also starting points for new ideas, experiments, and even new kinds of astronomy. They've redefined our understanding of time, mass, entropy, energy, and perhaps most hauntingly, information. They are no longer just strange predictions of Einstein's equations. They are testable, observable, and increasingly central to the quest for a grand, unified theory. Their visibility might seem contradictory. How can we study something that doesn't let light escape? Yet, it's precisely the surrounding chaos that makes black holes visible. Gas, dust, and even stars caught in their pull generate fireworks. On the way down, X-rays blaze from hot disks. Particles are accelerated to near light speed. Magnetic fields twist and snap like rubber bands. Jets of energy shoot out from the poles, extending light years into intergalactic space. These jets, observed in many galaxies, are among the most powerful known structures in the universe. They're not random chaos either. They emerge from the intricate interaction of spinning black holes, magnetic fields, and accreting matter. They suggest that black holes, far from being inert graves, are dynamic engines, converting gravitational potential into radiation and motion with astonishing efficiency. Consider this: when matter falls into a black hole's accretion disk, about 10% of its mass can be converted into energy. That's 10 times more efficient than nuclear fusion in a star's core. no other natural process is as energetically productive. For a brief moment, a feeding black hole can outshine an entire galaxy. And then there's spin. Most black holes rotate. This rotation isn't a minor detail, it's a defining feature. A spinning black hole drags the very fabric of space-time. Around with it, a phenomenon known as frame dragging. Imagine stirring honey with a spoon. The rotation pulls the honey into a whirlpool. Now imagine the honey is space-time itself. This region around a rotating black hole, where frame dragging dominates, is called the ergosphere. It lies outside the event horizon and presents some of the most fascinating physics imaginable. Within the ergosphere, nothing can remain stationary. Even light must move in the direction of the black hole's spin. But because this region lies outside the event horizon, it offers strange possibilities. In theory, it's possible to extract energy from a rotating black hole by plunging into the ergosphere, splitting a particle in two and escaping with more energy than you started with. This process, known as the Penrose process, is a kind of cosmic pickpocketing, the universe's only known legal way to steal from a black hole. And as wild as that sounds, it's just one of many exotic consequences of rotation. Rotating black holes also have different shapes. Instead of being perfect spheres, their rotation flattens them at the poles and distorts the event horizon. This distortion changes the gravitational dynamics around them, alters the location of stable orbits, and affects how infalling matter behaves. The mathematics describing rotating black holes, discovered by Roy Kerr in 1963, remain some of the most elegant and terrifying equations in all of physics. They describe not only how matter behaves near a black hole, but also how time behaves differently depending on direction. In extreme cases, time loops may form, a concept that has fueled endless speculation about time travel, paradoxes, and the possibility of closed time-like curves. Yet, despite the theoretical acrobatics, no credible evidence exists that anyone or anything has ever traveled through a black hole and returned. The laws of physics, as we understand them, suggest that such a journey would be a one-way ticket to oblivion. But what lies beyond the event horizon is still open to speculation. Is it a singularity, a bounce, a gateway? In some speculative theories, like loop quantum gravity, the singularity might be replaced by a dense but finite structure, avoiding infinite densities. In others, like the fuzzball proposal from string theory, the interior of a black hole is not empty, but filled with tangled strings of quantum information. These strings replace the classical idea of a singularity and potentially allow information to be preserved. It's a reminder that black holes aren't just objects in space. They're touchstones in a larger conversation about the nature of reality. They sit at the intersection of quantum physics, gravity, thermodynamics, and cosmology. In fact, black holes obey laws that look suspiciously like the laws of thermodynamics. This isn't an accident. The 1970s, Jacob Bekenstein proposed that black holes have entropy proportional to the area of their event horizon. Stephen Hawking extended the idea by showing that black holes emit thermal radiation, Hawking radiation, and therefore must have a temperature. These discoveries were revolutionary. They suggested that black holes aren't just cold, inert objects. They have heat, entropy, and thermodynamic behavior. And that entropy is enormous. The entropy of a black hole is the highest of any object of comparable size. It's not based on volume, as one might expect, but on surface area. 1 square centimeter of a black hole's surface contains more entropy than 1,000 libraries of encoded information. This leads to a profound insight. The maximum amount of information that can be stored in any region of space is proportional, not to its volume, but to its boundary. This idea that the universe is, in some deep way, holographic, has changed the way physicists think about space-time itself. It suggests that the universe might be like a three-dimensional projection from a two-dimensional boundary. In this view, black holes are not just exotic phenomena. They're clues to a more fundamental layer of reality where geometry and information are one and the same. So much of what we assume about the universe is up for negotiation in the presence of a black hole. Dimensions might be illusions. Time might be variable. Information might be physical. And space might be encoded in bits and boundaries, not distances and directions. And yet, black holes are real. Not just equations on a chalkboard, but objects we can measure, track, and watch. We can see stars whip around Sagittarius A*, can detect gravitational waves from mergers a billion light-years away. We can photograph the shadow of a black hole in M87. These aren't speculations. They're observations, evidence, reality. The universe, it turns out, is stranger than we can imagine, but not stranger than it is, and black holes are perhaps the strangest things in it. They are where science meets its limits, where light vanishes, time warps, and theories unravel. They are where we confront the unknown and try to measure it, where we peer into the abyss and it peers back with silence and gravity. Every deep look into a black hole is also a look into ourselves, a reflection of the limits of human thought stretched across the canvas of cosmic spacetime. These dark entities, born from collapsing stars or merging giants, are both the destroyers and the archivists of the universe. They consume matter, yes, but in that consumption, they record, distort, and possibly preserve everything they take. In the mystery is whether those records can ever be read again. The study of black holes is not isolated to the stars. It spills into laboratories, into computer simulations, into particle colliders, and even into philosophy. Some researchers believe miniature black holes might be created in high-energy events, perhaps in the early universe or even inside future particle accelerators. If such micro-black holes exist, they could reveal entirely new physics, perhaps even the shape and structure of extra dimensions. Indeed, extra dimensions are not just a science fiction indulgence. Some versions of string theory propose that there could be as many as 10 spatial dimensions, far more than the 3 we're used to. These extra dimensions might be curled up at scales too small to detect. Black holes, with their immense density, might be the only objects capable of exposing them. In such models, black holes might behave differently than expected. They might leak gravity into other dimensions or radiate more rapidly than predicted by Hawking. Detecting such behavior could offer our first indirect evidence for higher dimensional space. It's a long shot, but science progresses through bold questions, and black holes ask the boldest. But even without extra dimensions, black holes already stretch the boundaries of our understanding. Consider their role in galactic evolution. For decades, astronomers assumed that supermassive black holes at galactic centers were incidental, an optional accessory in cosmic architecture, but mounting evidence suggests otherwise. These behemoths seem to play a vital role in regulating star formation, influencing galactic structure, and possibly even controlling the growth of the galaxies themselves. It's a kind of cosmic feedback system. As matter spirals into a central black hole, it heats and energizes, producing powerful outflows, jets and winds that blow away gas and dust. This can suppress or trigger new waves of star formation, depending on the circumstances. In this way, black holes don't just anchor galaxies with their mass, they sculpt them with their energy, and their presence is more ubiquitous than we once thought. Nearly every large galaxy we've examined has a supermassive black hole at its core. Some are quiet, like the one in our own Milky Way, occasionally flickering with bursts of X-rays. Others are ferocious, devouring matter so rapidly they become quasars, pouring out more light than hundreds of billions of stars combined. These active galactic nuclei are not fringe phenomena. They are central engines shaping the very structure of the universe. Then there's the curious connection between a black hole's mass and its host galaxy. Observations have revealed a surprising proportionality. The mass of the central black hole is correlated with the mass of the galaxy's bulge. This relationship, known as the M-sigma relation, is not fully understood. How does a black hole, tiny on a galactic scale, maintain such influence over structures millions of light-years across? One possibility is that the black hole and its galaxy grow together, locked in a gravitational and thermodynamic dance that begins early in cosmic history. Another is that the outflows from the accretion disk regulate not just nearby matter, but the environment of the entire galaxy. In either case, it implies a kind of hidden order behind the chaotic ballet of stars and dust. But black holes aren't just found in the hearts of galaxies. Stellar mass black holes, those formed from the death of individual stars, are scattered throughout the cosmos. In our own galaxy, the Milky Way, astronomers estimate that tens of millions of black holes roam in silence. Most are invisible, betrayed only by their gravitational pull. But some give themselves away, siphoning material from companion stars. In binary systems, lighting up with X-rays in the process. These X-ray binaries offer some of the most detailed insights into black hole behavior. We can watch the orbits, estimate the mass, even measure the spin of the black hole. From these systems, we've learned that not all black holes are born equal. Some spin furiously, others barely rotate. Some have masses just above the neutron star limit, about 3 solar masses, while others tip the scales at 20 or more. And between stellar mass and supermassive lies a curious gap: intermediate mass black holes. For years, their existence was speculative. It's too heavy to be remnants of single stars, too light to sit at galactic centers. They were the missing link. In the black hole family, recent evidence, however, suggests they're real. Objects like HLX-1 and potential detections in star clusters point to black holes with masses between hundreds and thousands of suns. These elusive middleweights might be the building blocks of larger black holes formed through repeated mergers. Or they might form in dense regions where many stars collide. Either way, their discovery is reshaping how we think about black hole growth and about the structure of the early universe. That structure was anything but uniform. The early universe, hot and dense, birthed stars quickly, massive, short-lived stars that burned bright and died young. Some of these likely collapsed directly into black holes, skipping the supernova phase entirely. These primordial black holes might still roam the cosmos today, and in some models, they might even account for a fraction of dark matter, the mysterious substance that outweighs visible matter 5 to 1, yet reveals itself only through gravity. If primordial black holes do exist, they could be tiny, smaller than a mountain, but with the mass of a large asteroid. Or they might be massive, lurking in dark corners of the cosmos, ancient remnants of the universe's infancy. Detecting them would be challenging, but gravitational wave observatories and microlensing surveys are beginning to scan for signs. The mere possibility is staggering. It would mean black holes existed before stars, before galaxies, before light itself. They would be relics of a time when the universe was still figuring itself out, when quantum fluctuations were stretched by inflation into the seeds of structure. But whether black holes are ancient or newborn, silent or active, massive or modest, their behavior is governed by the same fundamental principles. They are the most extreme test cases of physics we have. They show us what happens when mass, time, energy, and space all collapse into a single entity. They are puzzles with pieces still missing, yet every piece we find reveals a little more about the nature of the cosmos. And if there's one thing black holes teach us again and again, it's humility. Our greatest theories unravel at their feet. Our most cherished assumptions break against their horizons. And yet, they reward our curiosity with more than mystery. They give us glimpses into new physics, new dimensions, and perhaps even new ways of thinking. They whisper, in their silence, that the universe is not done surprising us. At its deepest, truths may lie not in the bright and orderly, but in the dark and chaotic. That what we cannot see may shape what we see the most. As we descend further into the depths of black hole knowledge, it becomes clear that these cosmic enigmas are more than just celestial oddities. They are profound expressions of nature's dual identity, silent and violent, invisible yet monumental. They defy easy metaphors. They are not just giant vacuums or celestial drain holes. They are boundaries of understanding, of time, of the very laws that govern everything else. One of the most remarkable things about black holes is how they bend. Not just matter and radiation, but the very rules we rely on to make sense of reality. Even fundamental notions like causality, the sequence of cause and effect, begin to wobble near the event horizon. Time, that trusty arrow we follow from morning coffee to evening dreams, begins to curve, lag, and sometimes, depending on your trajectory, even stall. We've already glimpsed how clocks slow down near black holes. But this isn't just a curiosity. It's a serious constraint for anything that wants to interact with the rest of the universe. If you fall into a black hole, the outside world accelerates rapidly from your point of view. Stars age, galaxies rotate, empires rise and fall. For you, however, it might feel like an uneventful few seconds before space-time twists itself into irrelevance. The paradox is that from an external perspective, you appear frozen at the event horizon forever, dimmed, stretched, and smeared into oblivion. This oddity doesn't violate physics, it defines it. Time is not absolute. And black holes are not optional side characters in the cosmic narrative. They are central to the story. They dictate, in ways both subtle and overt, how matter gathers, how galaxies evolve, and even how the universe may one day end. Yes, the end. While we often think of black holes as endpoints, the final act in a star's dramatic collapse, they may also hold clues to how everything will eventually unravel. The universe is expanding, and that expansion is accelerating, driven by an unknown force we call dark energy. Over trillions of years, galaxies will drift apart, stars will die out, and black holes will be among the last objects standing. This far future epoch is known as the black hole era, a hypothetical stretch of time when all that remains are slowly evaporating black holes. According to Hawking's prediction, every black hole, no matter how massive, will eventually emit enough Hawking radiation to shrink and vanish. But this process is unimaginably slow. A black hole with the mass of the Sun would take more than 10 to the power of 67 years to evaporate. That's a number so big it makes the age of the universe, just under 14 billion years, look like a coffee break. During this incomprehensible stretch of time, black holes will radiate ever more faintly, shedding their mass into a cold, empty void. Eventually, when the last one fizzles out, the universe may settle into heat death, a state of maximum entropy where nothing more can happen, and even time itself loses meaning. But perhaps that's not the end. Perhaps, buried in the flicker of the final black hole is a bridge to something new, a hint, a bounce, a rebirth. Some speculative models suggest that the universe could recycle itself, collapsing into a singularity and then rebounding into a new Big Bang. In this way, black holes would not just outlast the universe, they would help launch the next one. This cyclical vision is ancient, echoed in mythologies as much as in modern equations. And while evidence is lacking, the idea reflects something important about how black holes continue to captivate us, not just as physical objects, but as metaphysical symbols. They represent limits, yes, but also potential. And this potential extends beyond science into the realm of imagination. Artists, writers, and philosophers have been entranced by black holes since the term was coined. They are metaphors for obsession, isolation, madness, transformation. They symbolize the unknown, the unreachable, the unknowable. They are the perfect narrative device, compelling, terrifying, and just out of reach. Science fiction has turned black holes into portals, prisons, computers, gods. In some stories, they are gateways to alternate dimensions. In others, they are sentient entities or weapons of unimaginable power. While none of this matches reality, it does reflect something deeper. Our instinct to fill darkness with meaning, to turn what we cannot see into what we cannot ignore. Even in hard science, black holes inspire creative leaps. The holographic principle mentioned earlier came not from wishful thinking, but from a crisis in theoretical physics. When confronted with the paradox of information loss, physicists turned to bold conjectures, building bridges between gravity, quantum mechanics, and thermodynamics. In the process, they may have stumbled upon an entirely new understanding of what space and time are. Some go further still. A few physicists now propose that space-time itself is not fundamental. Instead, it might emerge from deeper processes. Networks of entangled information, quantum bits interacting in complex ways. In this picture, a black hole is not a hole at all, but a complex state in a vast quantum system. The event horizon becomes a kind of statistical phenomenon, like the surface of a boiling pot, real but emergent. This view is deeply unsettling. It suggests that the geometry we take for granted is not the ground floor of reality, but a facade. That gravity, far from being a primary force, might arise from thermodynamics. That mass and motion are illusions, useful, yes, but secondary. And it all started because we tried to understand what happens when you throw something into a black hole. Black holes stretch more than just space and time. They stretch our ideas. They force us to reconsider what we thought was bedrock. They are the universe's most ruthless editors, deleting anything unprovable, highlighting every error, and daring us to revise. Yet, for all their strangeness, they remain part of the cosmic order. They obey conservation laws. They follow thermodynamic rules. They respond to gravity. Their existence is not chaos, it's consistency taken to an extreme. And here's perhaps the greatest paradox. The more we understand black holes, the more we realize we don't understand the universe. Every answer opens 5 new questions. Every discovery reveals a deeper mystery. They are not ends. They are invitations. An invitation to explore, to question, to reach, to ask what lies beyond, and then to go looking, even if we know we can't come back. And in this way, black holes are not about falling into darkness. They are about climbing toward light, one photon, one theory, one idea at a time. The deeper we go into black holes, the more we realize we're not just studying objects, we're unraveling the very threads that hold reality together. With every simulation, every observation, and every wild theoretical sketch on a physicist's whiteboard, we inch closer to something elusive. Black holes are like the footnotes of the universe, cryptic, dense, and sometimes more illuminating than the main text. They demand we reread everything we thought we understood. Let's return to something that seems simple at first, but becomes profoundly strange under the influence of a black hole: the concept of distance. In our everyday lives, distance is straightforward. 1 meter here is the same as 1 meter over there. But black holes rip this idea to shreds. Inside the warped spacetime they create, the very act of measuring distance becomes subjective. A meter might stretch into infinity or collapse into nothing, depending on your frame of reference. As you fall toward a black hole, your perception of space and time morphs. The direction labeled inward becomes increasingly complex. And at a certain point, known as the event horizon, something extraordinary happens. The roles of space and time switch. Time becomes a direction you can't avoid, like falling down a waterfall. Space becomes time-like, dictating not where you go, but when you must go. There is no pause, no turning back. Every possible future leads only to one place, the singularity. This reversal isn't just a curious twist. It reveals a deeper symmetry at the heart of spacetime. And it hints at something even stranger, that the inside of a black hole might not be a place in the way we understand it. It might be a sequence of inevitabilities, a progression of cause and effect so tightly bound that they form a singular fate. And what of the singularity itself? Is it truly a point of infinite density, or is it simply where our equations give up? Most physicists suspect the latter. The singularity might not be real in a physical sense. It might be a placeholder for laws we haven't yet discovered. A sign that we need a quantum theory of gravity, one that can unify the smooth curves of relativity with the jittery chaos of quantum mechanics. There are many candidates for such a theory. String theory proposes that everything is made of vibrating strings, and that gravity emerges from the behavior of certain kinds of strings. Loop quantum gravity suggests that spacetime is made of tiny loops woven into a fine fabric that resists infinite compression. Others explore ideas like causal sets, non-commutative geometry, and emergent spacetime. Each of these attempts brings new language, new math, and new metaphors. But none has yet delivered the full picture. The black hole, sitting at the center of all this theoretical noise, remains silent. It keeps its secrets even as it tempts us with flashes of truth. But the silence may not be permanent. Gravitational waves, ripples in space-time itself, are now letting us listen to black holes in an entirely new way. When two black holes spiral together and merge, they send out pulses of pure distortion. These signals, first detected in 2015, carry the unmistakable signature of black hole interactions: a slow crescendo, a peak, and a fading ringdown. It's music, in a way. Not sound in air, but the vibration of the universe. And like any good music, it tells a story. From these waves, scientists can determine the mass, spin, and even the shape of the black holes involved. We're not just seeing the universe, we're hearing it too. And the implications are stunning. We've already detected black holes more massive than we thought possible. Mergers that suggest entirely new formation pathways. Signals from billions of light years away. Gravitational wave astronomy is young, but it's already rewriting the black hole story. In time, it may even help answer the most profound questions. Could we detect signs of quantum behavior in black hole mergers? Could echoes in the waveforms hint at structure inside the event horizon? Could we spot deviations from general relativity, pointing the way to new physics? The future of black hole science may be written not in light, but in vibration. And not all vibrations are fast and violent. Some are slow, steady, background hums. The cosmic microwave background, for instance, is a faint afterglow of the Big Bang. But what if there's a gravitational equivalent? A soft wash of waves from countless black hole mergers over cosmic history. Detecting that background could open a new window into the early universe, into the very formation of black holes themselves. We might finally trace the lineage of supermassive black holes. Did they grow slowly over billions of years? Or were they born big, as direct collapses from early gas clouds? The clues lie in the quietest corners of the cosmos, and black holes are nothing if not quiet, except when they collide. Of course, some questions remain maddeningly stubborn, like the firewall paradox. If information is preserved outside a black hole, then something must happen at the event horizon to encode it. but that might require a searing wall of high energy. Particles, an idea that clashes with general relativity's smooth predictions. So, which theory bends? Quantum mechanics or gravity? Both have stood unchallenged for decades. Yet somewhere in the folds of a black hole's event horizon, one of them may blink first. And maybe that's why we keep staring into the dark. Not because we think we'll conquer it, but because it's where the edges of knowledge touch. Where theory meets observation. Where the chalkboard meets the telescope. In a sense, black holes are the ultimate editors of the cosmos. They strip away the fluff. No electromagnetic distractions. No surfaces. No solid cores. Just mass, spin, and charge. And even these properties are subject to simplification. The no-hair theorem tells us that black holes, no matter how messy their birth, settle into a state defined by only a few measurable traits. They don't remember what made them. They erase history. Or do they? If information is truly conserved, as quantum theory insists, then the past must be encoded somehow. In the quantum flutter of the event horizon, in the subtle correlations of Hawking radiation, in patterns we haven't yet deciphered. So maybe black holes don't erase history. Maybe they compress it, encrypt it, bury it beneath layers of curved spacetime and thermodynamic fog, waiting for someone or something to crack the code. And even if we never decode it fully, the pursuit itself changes us. It pushes the boundaries of mathematics. It refines our instruments. It reshapes how we think about time, space, and existence. Black holes stretch space. They stretch time. But perhaps their greatest feat is how they stretch the mind. As we now approach the furthest edge of what is known, the terrain around black holes becomes more philosophical than physical, more conceptual than concrete. And yet, even in this strange borderland where science bends toward speculation, the data keeps arriving, the observations keep sharpening, and the shadows of these cosmic monsters continue to reveal structure, motion, and, perhaps most startlingly, order. Despite their apparent chaos, black holes are not lawless. In fact, they are the strictest accountants in the cosmos. They obey conservation laws with a rigidity that defies their mysterious appearance. Every particle swallowed, every ounce of mass absorbed, every pulse of energy collected. Nothing disappears without accounting. The universe doesn't tolerate cosmic free lunches, even when it comes to something as extreme as a singularity. But singularities, as we've seen, may not be the final word. They are signals, not endpoints. Signals that our current tools are insufficient. Relativity provides the scaffolding. Quantum mechanics gives the ingredients, but somewhere in the heat and twist of a black hole's core, both languages begin to contradict each other. We need a new grammar of physics, and black holes are writing it one paradox at a time. The most tantalizing of these paradoxes remains the information paradox. It refuses to settle, despite decades of theoretical battle. If Hawking radiation truly carries no information about what fell in, then quantum mechanics is in serious trouble. But if the radiation does somehow carry information, then general relativity's description of the event horizon, smooth, indifferent, absolute, must be incomplete. One of the most compelling recent attempts to resolve this comes from the concept of quantum entanglement. If particles inside a black hole are entangled with particles outside, perhaps information can leak out in subtle, non-thermal ways. This leads to mind-bending constructs like entangled wormholes, or E equals EPR, a conjecture that Einstein-Rosen bridges wormholes and Einstein-Podolsky. Rosen pairs entangled particles are two sides of the same coin. If true, this would imply that spacetime geometry and quantum information are fundamentally linked. That when particles are entangled, they may literally be connected by tiny, microscopic threads of spacetime, wormholes too small to traverse, but still present in the structure of reality. In this view, black holes become knots in this threadwork, places where entanglement becomes dense, saturated, and geometrically extreme. This is not fringe speculation. It is, in some sense, a natural extension of where theoretical physics is headed. We are no longer looking at the universe as a giant machine made of particles. We are beginning to see it as an ocean of information, where matter and energy are just emergent patterns in a deeper informational substrate. And here, black holes offer a striking clue: the Bekenstein-Hawking entropy formula linking surface. Area to entropy suggests that the true content of a black hole, its inner state, is encoded on its outer surface. It's like having a book where every page is stored on the cover. This breaks our classical intuitions. We expect volume to contain the story, but in black holes, it's the boundary that holds the tale. This principle, known more broadly as the holographic principle, might apply to the entire universe. Our three-dimensional world may be a projection from a two-dimensional reality at its boundaries, perhaps even from the cosmological horizon of the observable universe. In this holographic universe, what appears to be depth is encoded in surface correlations, and what appears to be inside is an illusion crafted from the outside. If that doesn't send a chill down your spine, remember, this idea isn't just metaphysical musing. It's grounded in the very behavior of black holes. The entropy-area relationship, the strange dance of information, the thermodynamic parallels, all of it supports the notion that boundaries in the universe are more fundamental than interiors. It's a radical concept. Radical ideas are nothing new in the history of black hole physics. It was once thought absurd that light could not escape an object. It was once shocking that gravity could bend time. It was unthinkable that the vacuum could boil with particles. Yet here we are, navigating a cosmos where every one of those impossibilities is a fact, and the implications ripple outward. Black holes not only shape galaxies and bend space, they may determine the limits of computation itself. There is a theoretical limit to how much information any region of space can store, known as the Bekenstein bound. That limit depends on the surface area enclosing the region, not its volume. In other words, a sphere of data hits its storage maximum, not when it's full, but when its surface is saturated. This sets the stage for deep connections between gravity, thermodynamics, and information theory. Some even speculate that the ultimate laws of physics may be algorithmic, rules about how information can flow and transform rather than how particles push and pull. In such a picture, black holes aren't glitches or dead ends. They are operating systems running at full capacity with every bit of data accounted for. This might explain why black holes are so simple on the outside. All the rich chaos of formation, stellar death, galactic collisions, plasma storms, gets boiled down into a few key descriptors: mass, charge, and spin. The complexity gets compressed, encoded, encrypted. What looks like loss is actually translation. And as our observational tools improve, we're starting to read those translations. The Event Horizon Telescope, using a planet-wide network of radio dishes, gave us the first image of a black hole's shadow. That image wasn't just a technical triumph, it was a symbol. Proof that black holes are not abstractions. They cast shadows, curve light, and draw bright halos in glowing matter. But the image was only the beginning. In the years to come, we will resolve more detail. We may see turbulence in accretion disks, map the orbits of individual gas clouds, and perhaps even measure the polarization of light twisted by extreme gravity. Each new pixel brings us closer to understanding how black holes interact with their environments, and how their seemingly featureless boundaries might hold the fingerprints of the universe's hidden code. And while black holes may be the stars of this show, They are not isolated actors. They interact constantly with nearby stars, with galaxies, with dark matter halos, with interstellar gas. These interactions tell us about the life cycle of matter, the flow of energy, the scaffolding of cosmic structure. In galactic centers, for example, black holes can both feed and starve. When active, they blast jets that sweep away gas, halting star formation. When dormant, they let matter accumulate, paving the way for new stellar nurseries. They're like cosmic thermostats, sometimes stoking the fire, sometimes turning down the heat. And on a grander scale, black holes may influence cosmic structure itself. The distribution of dark matter, the shape of galaxy clusters, the patterns in the cosmic web. Every filament and node may have felt the gravity of black holes or responded to the energetic push of a quasar in its youth. From the smallest scales of quantum foam to the largest filaments of the cosmic web, black holes cast a long shadow, not just in mass or momentum, but in meaning. They are the universe's punctuation, marks, sometimes commas, sometimes colons, often full stops, but always with the promise that another sentence, another discovery, is coming next. There is something uniquely poetic about the way black holes conclude stories. Stars that shine for billions of years, burning hydrogen into heavier elements, living dynamic lives across vast stretches of cosmic time. Eventually, they collapse, yielding to gravity's relentless grip. And from that collapse emerges silence. A singularity wrapped in darkness. A body whose surface does not reflect, whose core defies inspection, whose presence warps everything around it without offering anything in return. And yet, in that silence, the universe speaks. Black holes are not the end of understanding. They are the beginning of deeper questions. They are where our classical certainties fall apart and our quantum imagination begins to spark. They are where data meets paradox, where observation meets interpretation, where knowledge must humble itself before the unknown, and they are not as silent as they appear. With gravitational wave detectors humming across Earth, we can now hear the collisions of black holes from across the cosmos. Those waves, once just theoretical predictions, are now recorded with astonishing precision. Each chirp from space is a record of a massive invisible dance to titans orbiting closer and closer, until at last they merge. No explosion, no light, just the echo of space-time being rearranged. With every detection, our map of the universe becomes richer. We've observed black holes merging with other black holes, with neutron stars, even candidates for intermediate mass black holes. These observations are like sonar pings in the ocean of deep time. They reveal not just what's there, but how it moves, how it evolves, and how it connects to everything else. Even more thrilling is what we haven't detected yet. Black hole mergers at high redshift from the early universe. Exotic compact objects that might mimic black holes but behave differently. Deviations in the ring-down signals that could hint at new physics. The silence of black holes is not empty. It's pregnant with potential. Meanwhile, other instruments continue their pursuit of light. The James Webb Space Telescope, the Chandra X-ray Observatory, the Atacama Large Millimeter Array, all of them contribute pieces to the puzzle. By watching matter swirl around event horizons, we can estimate spins. By observing flares, we infer magnetic fields. By tracking the motion of stars near galactic centers, we confirm masses with pinpoint accuracy. All of this data flows into models, complex simulations running on supercomputers, recreating the ballet of plasma, gravity, and relativistic physics. These simulations are not just visualizations. They are predictions. They tell us what to look for. They refine our search. They make the invisible slightly more visible. And still, the questions grow. Do all black holes have event horizons? Could there be exotic alternatives, gravastars, boson stars, wormhole mouths, that mimic the effects of a black hole without being one? If so, how would we tell the difference? Would the gravitational waves from such objects ring differently? Would the light curve from infalling matter look subtly wrong? We are beginning to ask these questions seriously, and the answers may reveal cracks in our most cherished theories. But perhaps the most important question of all is not physical, but epistemological. How do we know what we know? What can we truly infer about the interior of a black hole when all our measurements must stop at the event horizon? What does it mean to say something exists if it cannot be directly observed? In this way, black holes are not just astronomical phenomena, they are philosophical provocateurs. They force us to revisit old ideas. What is information? What is space? What is time? What is reality? Some researchers now believe that black holes may be the most efficient objects in the universe for storing information. Others suggest they are the ultimate quantum computers, processing inputs in ways we don't yet understand. Some go further, proposing that the entire universe may function like a black hole, bounded, finite, with an informational content defined by its surface. It's an audacious idea. But then, so is the idea that gravity could bend light, or that mass could slow time, or that two black holes could spiral into each other, send out a ripple we could detect with lasers on Earth. Each of those ideas once sounded impossible, and now they're facts. So we keep pushing. We keep building new detectors, refining old models, collaborating across continents. The study of black holes has become one of the most global, interdisciplinary endeavors in science. It draws on astronomy, physics, computer science, mathematics, even philosophy. It bridges the very large and the very small, the very old and the eternally new. And for all the mystery, there is a quiet clarity at the heart of it. Black holes remind us that knowledge is not a static thing. It's a curve, always bending toward the unknown. They remind us that even the darkest regions of the universe are not beyond reach. That silence can be full of signals. That darkness can be a source of light. So when we stare into the shadow of a black hole, we are not just seeing absence, we are seeing structure. We are witnessing the triumph of theory meeting evidence. We are watching humanity stretch its understanding across impossible distances, into impossible realms, and still come back with something true. This is not just a story of gravity. It's a story of curiosity, of persistence, of listening closely to the quietest parts of the universe and finding, again and again, that they have something to say. Thank you for spending this time with us at Slow Science Sleep, the channel where deep science meets deep rest. We hope this journey into the heart of gravity was fascinating, and we're truly sorry if all this cosmic drama made it harder for you to sleep instead of easier. If you enjoyed the video, please like, subscribe, and leave a comment telling us where you're watching from and what time it is in your part of the world. Your feedback helps us grow and reach more people who are curious, thoughtful, and maybe just a little sleepy. Now, as the stars spin and space curls gently around you, we invite you to close your eyes, take a deep breath, and listen to the soft sounds we've prepared. Let them guide you away from singularities and space-time into the peaceful gravity of dreams. Good night.